We're rolling, so let's get started.
Hi.
Go ahead and get out your notebooks. Everybody say hi to Pima Community College.
Hi, Pima.
The person who's watching this is not a bro, she's a lady.
Stop, sis.
That'll do. Okay, so we are starting on the next chapter. We are starting on chapter 5. So up to this point, what do you think what have we studied really? What kind of math? What have we been looking at? Derivatives. And what do derivatives represent?
The opposite.
They represent slope, they represent rates of
Change.
okay. Well, today we are moving away from derivatives. Imagine that.
It's not. Why are you doing
Today,
No.
today we're going to be looking at accumulation. We're going to end our objective is to estimate the area under a curve. It's the wettest time of the day.
This should make $30
Then you'd miss out on all the cool calculus. So, you're breaking my heart. Okay, so go ahead and copy down the title and objective of today's lesson.
What about
Oh, the homework. I'll take the homework back at the end of class. Well, I do stay after on Thursdays. Okay, so I still see some desks without notes on them. You guys need to be taking notes.
They're not here.
I see a title and objective. You need to get that and be writing that down.
paper in the room.
As a matter of fact, I do.
I need two extra.
Okay. So, accumulation. Now, up to this point, we've been looking at instantaneous rates of change, but we're moving on to something totally different. Now, derivatives tell us how quickly something is changing at a given instant. So, what is accumulation? What does it mean for something to accumulate? To happen? Okay, so it means like build up. So accumulation means like to build up. Anything else? Any other ways we can maybe think of accumulation? What do I mean when I say that? So just really quick, raise your hands if you have never seen this word before. You know what it means. Okay. Well, to accumulate means to pile on. So to add a whole bunch of stuff onto stuff already there. So for example, if you have a big pile of sand and you're tossing sand on it, the pile is going to accumulate and you're going to get more of it over time. So accumulation means to build up, but fundamentally, it means that we're adding onto it, right? So all the changes that have happened to it are all combining together to result in a new pile. That's what accumulation means. So it means to add up all of the changes that that have been done to something. Make sense?
Yeah.
Okay. Okay, so let's try an example of what I mean when I talk about accumulation, or another way of putting it would be cumulative change. Okay, so let's say that I'm driving to Flagstaff. I always use Flagstaff in my examples. I like Flagstaff. So we're driving to Flagstaff. So how fast do you think should I be driving? Say I heard 100 miles an hour, I heard 5 miles an hour. Let's go for something else somewhere in the middle there. Let's say I'm driving the speed limit. Okay. You have a license? So.
Do you have a license?
So we are driving to Flagstaff at 65 miles per hour. Let's make it 60 actually, to make our math a little easier. So this is 60 miles per hour. What does this represent? Yeah, this is representing our rate of change. Yeah? So let's go ahead and ask ourselves the question. How far will we travel in 3 hours? Do we get 60 times 3 is 180? Okay, so we'd go 180 miles, right? Or, if we should write our units, that's 60 miles per hour times 3 hours. Our hours cancel, leaving 180 miles. Fair enough? So what did we just find? Well, we started with how quickly we're traveling, but we were able to figure out our total distance traveled. So as we're driving, we're eating up the miles underneath our feet, and when we're done with our journey, we've accumulated a certain amount of distance traveled. So this 180 miles that we have here would be the cumulative change. You could think of this as the I need to. You can think of this as the cumulative change or the total result, maybe, of our speed. See what I'm saying? Okay, John, you need to be taking notes. Okay, so this is fair enough, right? You've done this a million times. You've done this a million times before. That's pretty obvious. Now let's go ahead and look at this in a way that maybe you haven't looked at it before. let's look at this problem graphically. So let's say that I have a graph here.
Or are you supposed to turn the homework from your thing?
We'll turn it at the end of class today. It was due today. Okay, so let's go ahead and try looking at a graph of this situation. Now on the horizontal axis, we'll go ahead and put time. It's our independent variable. How fast we drive does not change the flow of time around us, mostly. And what should I put up here, you think? Distance is what, we might be most used to thinking about, but we weren't given distance. We were given speed. So we'll go ahead and put speed, or what's probably a better word for speed? Starts with a V? Velocity. So we'll go ahead and put velocity on this side here. Okay, what's our unit for time?
Second.
What's our unit?
Oh,
Hours. What's our unit for velocity? Miles per hour. Okay. So let's go ahead and graph our speed over time. So we're graphing. Well, let's see. Is our speed changing at all?
No.
No. So what is our speed for this journey? 60. So we'll go ahead and call this 60. So is our speed going up? Is it going down, or is it staying constant? Constant. Okay. Now, for how long are we driving?
3 hours.
3 hours. Okay. Okay. So, what shape did I just make? This looks like a rectangle to me. So, let me ask you another question. What is the area of this rectangle? It's 180, isn't it? Not only that, how did we get 180? How did we do that? Okay, so how long is it? 3.
3 hours long.
It's 3. Its length is 3 hours, and what's its height? 60 what? 60 puppies? Its height is 60 miles per hour.
Alright, just call it 60. So.
Certainly would make math much cuddlier. Okay. So, 3 times 60 is 180. Our hours cancel out, leaving us with an area of 180 miles. Well, isn't that interesting? The area underneath our graph ended up being the same as our cumulative change, our total distance traveled. Do you think that only works for like 3 and 60? Or will that work for no matter how fast I'm going or no matter how far I'm traveling?
Yeah.
Yeah, it should work. I don't see any reason why it wouldn't.
Because your mom.
So, do I actually, when we drive someplace, do we start at 60 miles an hour and drive at exactly 60 miles the entire distance and then we stop instantly?
No.
No, we get fast, we speed up.
You can if you
Take
use
a
the
key.
power of imagination.
That's pretty calculus. Anyway, imaginary numbers? No?
Yeah.
So we start by speeding up, getting up to speed, then we level off for a ways, and then we slow down to a stop. So let's look at a situation that's more like that. Well, before that, so let's go ahead and write down what we learned here. So the area under this line the area under the curve, or under the line, equaled our accumulated change. Or in this case, total distance. Does that make sense? So let's try looking at one that's a little different. Okay, I'm going to erase this. We all good? Okay. Okay, let's say that a vehicle has an acceleration of, let's say, what are the units for acceleration usually? You remember this one? For speed, it was meters per second. It was the velocity over time, which added up to meters per second squared, or distance per time squared. So let's say that we're driving, that our vehicle has an acceleration of 10, let's say, miles per hour squared.
Does an acceleration have 1 L?
I have no idea how many L's acceleration has. I'm assuming you're right.
Okay.
A vehicle has an acceleration of 10 miles per hour squared for 2 hours. Drives at a constant speed for another 2 hours. Then slows down with an acceleration of, before I write this down, when we slow down, is our acceleration positive or negative?
Negative.
Negative. Speeding up means we have a positive acceleration, slowing down has a negative acceleration. So he slows with an acceleration of, let's say, negative 20 miles per hour squared for 1 hour. How far did the vehicle travel? Okay, let's see if we can figure this one out. Well, let's go ahead and draw this situation using the same similar graph as right there. So, oh, I should say it starts from rest. That's important. Starting from rest. Okay, so when we're starting, so let's go ahead and do the same graph speed on the vertical axis, time on the horizontal. Or velocity, rather. Okay. So what's this going to look like? So where are we? So what's our starting speed? When our vehicle's at rest, how fast is it going? 0. So now it's accelerating. So what's going to happen? I'm going to draw a line. Is it going to be going up? Is it going to be going down? It's going to be going up. Now, what is the slope of that line going to be? Slope is going to be our acceleration, 10. We learned this earlier. We learned this earlier on in the class when we were talking about speed and derivatives. Acceleration is the derivative of velocity, so acceleration is the slope of velocity. So since we're graphing velocity, that means that we need to draw a line on the slope of 10. So for each 1 hour that passes, how far up does my speed go? Okay, so for how many hours does it accelerate? For 2 hours. So 2 hours, it goes up by 10, then up again to 20. Okay, fair enough?
Mm-hmm.
Does that make sense what we're drawing so far? Now, for how long does it, now it's going to drive at a constant speed. So what's its slope going to be?
Flat.
It's going to have a flat slope for 2 hours. 1 and 2. Okay, then what does it do?
Slow down.
It slows down. So what's going to happen to the slope? Or will the slope be positive or negative or 0?
Negative.
Negative. And what's its slope going to be? Negative 20. So when we go over 1 hour, how far down are we going to go? Back down to 0. Okay. This isn't particularly realistic. Nobody accelerates a vehicle for 2 hours. But, it's a good little illustration of what's going on. So, so how can we find out how far the vehicle has traveled? We just learned the area under a line equals our accumulated change. So here, the total distance.
Is that proof though? You gotta prove it first.
We have not proven it. I do not actually have a proof here, so we're going to have to take my word for it. If I had a proof, I would give it to you. We will be we'll be doing proofs similar to this later on once we have more advanced tools. For now, you're going to have to take my word for it.
Like we're gonna have to prove functions in the AP Calculus exam.
Probably not.
That's
So-
how we're doing it.
Because you need to know what you're doing. The proofs are still useful.
What time do you
Okay, so anyway, we need to know how far the vehicle traveled. So the distance our vehicle traveled, this is our accumulated change. All of the changes that have been done to the vehicle all add up to its new position. And we can find that with the area under the curve. So how are we going to find this area?
You use the formula to find the area of the trapezoid?
Well, this isn't. This is a trapezoid, but the area for a symmetrical trapezoids might have a simple formula, but this one we're going to have to break up into chunks. Are these two triangles the same? Nah, this one has. How long is this base?
2.
Okay, and how long is this base?
1.
So we're just going to have to break it up into different shapes, aren't we? So let's go ahead and just find the area of each of these shapes. What's the area of this triangle going to be? How'd you get that? Okay. So, but how did you get that? What's the formula? Yeah. right, so everybody, what's the formula for the area of a right triangle? 1/2 base times height. Everybody say that again for me. Everybody.
1/2 base times height.
Sweet. Okay. So the area of this thing is going to be 1/2 base times height. And the base is what? 2 hours. And what's its height? 20. So it's 1/2 times 2 times 20. 1/2 times 2 times 20 is 20. So we know that the area of this chunk is 20. Okay, now what's the area of this rectangle going to be? And how'd you get that? So what's the formula? Base times height? And yes, same thing. Length times width, base times height. So the area of a rectangle is length times width. So what's its length? 2. And what's its height? 20 to give us a total area of what? Now for the last one. What shape is this? Okay, so what longs its base? 1, and what? How tall is it? So what's 1/2 times 1 times 20? 10. So let's add them all up. 20 plus 40 plus 10 is how much? 70 bananas? 70 miles. Fair enough?
So we assume that the vehicle was a T model.
If that. So we can see how we can find accumulated change by finding the area under the graph. So is this a particularly realistic graph though? How likely is it that we're going to accelerate perfectly evenly for 2 hours, then drive at a perfectly constant speed, then decelerate, then instantly go to a perfect deceleration? Is that something that vehicles do?
How about trains? Electric trains could.
They still wouldn't be doing it perfectly. It might get close, but never perfectly. So let's try looking at a situation that might be a little more realistic. This is way faster than a Mars rover. Mars rovers travel no more than a few meters every day. What? Juno? Juno was a probe to Saturn, I think. Well, since it's a spacecraft, it travels a lot faster. Okay. Go for it. Okay, so let's go ahead and try graphing something that maybe looks a little more realistic. So, what's our starting speed going to be? And if I press on the gas, am I going to accelerate instantly to some constant acceleration?
No.
What's my starting acceleration going to be? 0, but I'm going to slowly speed up, won't I?
Yeah.
Then when I get up to speed, I can let off the acceleration and start to slow down. Go to a constant speed for a while. And then I need to decelerate. So if I'm a good driver,
Why people say decelerate? It's de-accelerate.
it is decelerate. Decelerate is the correct term.
It's de-accelerate.
You are incorrect, John.
If you're Larry, then it just accelerates and decelerates constantly.
Of course, a better way to say it would be positive and negative acceleration. Anyway,
Negative acceleration.
So how could we estimate how far we've traveled. Oh, I should put the axes here. So we need velocity and time. So how could we estimate the total distance traveled for this vehicle? Let's say that from beginning to end, it was, how many hours do you think? 10, make it nice and easy. Let's say their velocity goes up to, again, let's keep it nice and easy, let's say 20. So how could we estimate it here? Again, let's just try to estimate. Are we going to like figure this out exactly necessarily? Just looking at just given a graph like this, but we can get a good idea. How can we make an estimation?
You break it down into shapes.
We could break it up into shapes. So we, instead of just trying to figure out like the area of this freaky, I don't know, upside down bowl, we could break it up into shapes. How would you guys break it up?
There would be a square in the middle.
You think maybe like a big old square in the middle, and then we could break it up into triangles?
We do this during derivatives.
We did something similar during derivatives. Maybe something like this, something like this. Do you think we'd get a decent estimation for the area? Would it be perfect?
Close.
No, it wouldn't be
No.
perfect.
What could we do to get a better estimation?
Derivatives.
We could do math to get a better estimation. Well, let's go ahead and just start by using this situation, try to estimate the area under this curve. So, if it's 10 hours here, this would be like, let's say this is 4, this is 7. So what would you estimate the area of this, what would the area of this triangle be?
4 times 4 is 40. It would be 40.
Yeah, so 1/2 of 4 times 20 is 40. What about this segment here? Okay. This segment here? So 3 times 20 times 1/2 is 3 times 10, which is 30. So we end up with a total estimated distance traveled of what? Okay, so that gives us an approximately 130 miles.
Thank you.
Oops. See, let me check the time of the recording. Okay, so we figured out that we can estimate the area under these curves, under funky looking curves, by breaking it up into shapes. Okay, so now let's go ahead and try one that's a little less hand-drawn, something with an equation that's actually given to us. X squared, I heard? Let's stick with a positive one, keep things simple. Okay, need a moment?
Yeah.
Okay, I'll give you about 20 seconds to copy down what you can. The positive one is the one that opens out. The negative is the one that's upside down. Okay, so everybody needs to have this copied down. going to go ahead and move to the other board, actually.
For it being blocks. Here. How much would that used to be for me to go for this? Would we go for
Okay.
this?
So let's go ahead and try to do something like this again. Let's estimate the area under the function f of x equals x squared. Between, let's say, 0, between x equals 0 and x equals 4. Okay, so what's a parabola look like? That's a good question. So, that's a very good question indeed, and I will answer that question after we draw a parabola. Okay, so a parabola is kind of the swoosh. So it goes up. So when x is 1, what's the y on a parabola? Remember, because so y equals x squared, so if I plug in 1, what's y going to be? Okay. Actually, I need a different scale, so I'm going to make this one actually work decently. So I go over 1 and up 1. There's our first data point. If I go over 2, how far up do I go? 2 squared is 4. Go over 3, how far up am I going?
9.
If I go over 4, how far up am I going?
16.
16. 9, 10, 11, 12, 13, 14, 15, 16. Okay.
It's got to be the derivative.
What is the derivative?
It should be derivative.
Should and could have nothing to do with math. Okay, there we go. So I have something that looks vaguely like a parabola if you squint, or maybe hit yourself in the head a couple times. So I say I want to find the area under the curve. Now what do I mean by that? When I say area under the function or under the curve, I mean the area between the line and the x-axis. Okay? Oops. There we go. So I'm trying to find the area of this shape here. So, how can we estimate this area, you think? We could probably draw a great big old triangle. Now, if we do that, we'd actually be finding the average change over time. That would be the line here would be our average speed. And so we'd be using our average speed to find it. But let's try to refine it down a little bit. The triangle would be kind of the biggest, grossest, least accurate thing we could reasonably do. Let's try to break it down a little bit further. We're not going to be using any derivatives today.
One rectangle and 2 triangles.
So you mean like a triangle here? I don't quite see how we could break it up into like a rectangle and triangle.
Well, it could be too that the way I drew mine, it's a little bit more stretched out so I can see it a little better.
Yeah.
But
Well, let's. So I mean, you know, we could. I mean, honestly, we could draw anything we want as long as we can fit it in here and we make it work. But let's try to keep something nice and simple. What's the easiest area shape to find the area?
Square.
Like rectangle, length times width, yeah? So let's just break this up into rectangles. Okay. And let's keep pi out of this. I'm going to try to
Double helix.
a double helix. Goodness gracious. It must be genetic. Anyway, so let's go ahead and try breaking this up into rectangles. Now, will our rectangles fit perfectly? No, they won't fit perfectly. So now what's probably the best way to draw these rectangles? What do you think I should do? So let's...
Little tiny bar graphs.
Okay, let's kind of make it look, yeah, kind of like a bar graph. That should make things nice and easy.
I read about this in a book.
Probably. So if we start here, where should we go, you think? Up? Up until what? Until I hit the line. Cool. Awesome. Right there.
Then even intervals.
Okay, so then how can I finish my rectangle?
Go across
Which way's across? Left or right?
Right one.
Right, you think?
Right one.
Like
Just a
that?
little bit.
Yeah.
Just a little bit.
Okay, right one, so that now I can, like, to the edge of the next rectangle.
Yes.
Okay, so now let's go ahead and draw the next rectangle. We go up.
Up. Then it goes
Okay.
same thing.
Then we go right by one.
South.
Then we go up until we hit the line. Then whoop, right there. So
I have to get smaller and smaller. You gotta get a lot smaller than that.
okay. So now now we've broken this up into how many rectangles here? 3. Well, sort of. I can kind of see a fourth one. What if we start right here and go up until we hit the line? Well, we'd still have a rectangle. It just would have a height of 0. So, you know, see where I got my fourth rectangle right there? So what's the area of each of these rectangles going to be? It's going to vary. Okay, what's the area formula for each of them? Length times width. Okay. Do they all have different widths, or are they all the same width? They're all the same width, right? Okay, so what's the width of this one? And this one? 1, 1, 1, and 1. Okay, so what's the length of each of these? How tall are these triangles? Well, the first one right here, how tall is this one? 0, okay. So the area of this triangle is 1 times 0, which gives us 0. Now, how tall is this one?
It's 1 by 1.
Let's ignore my lines because they're terrible. So what's my x value right here?
1.
So if my x is 1, what's my y? It's 1 squared, which is 1, right? So this rectangle has an area of 1 times what? 1. Now the next one, how far up are we going?
4.
We go, to get to this rectangle, we go right by how far? We go 1 and then 2, right? So how tall is it? 4. 2, our x is 2, so 2 squared will give us our y. So this is going to be 1 times 4. Okay? Now, how tall is this last one? 9. So we want to relate by 3, up by 9, which means that's going to be 1 by 9. And what's 1 times 9? 9. Okay. So now we can how can we find the total area of all these then? Add them up. What's 0 plus 1 plus 4 plus 9? Let's see. 10, 4, 14.
10, 4.
Okay. So is that the exact area?
No.
Nah. Is that an overestimate or an underestimate? That's an underestimate, isn't it? Because, you know, we're missing all these chunks here.
How about overestimate and equal overestimate?
Okay, well, that's a fair point. If this is an underestimate, how can we maybe do something that would get us an overestimate?
When you draw a rectangle, first one, instead of that line on the bottom with the area of 0, you go all the way up to the second rectangle.
I don't quite follow, but I'll go ahead and draw. I think I see what you're saying. Let's go ahead and draw another one, and you can help me out. Make sure I'm drawing what you're making it correctly.
No.
No, well, I just want to draw another one so we can leave the old one there to compare. So don't go messing with it. Hey, don't go messing with it. Josh, take a seat.
You know what I'm saying now?
I do know what you're saying now, but take a seat anyway. Okay. This one will be a little bit rougher. Yeah, I know. It's already not exactly yet. Okay, so 1, 2, 3, 4. Okay, so before we started at each point and we went up until we hit the line. So we went from the left, hit the line, moved right, went up, hit the line, moved right, went up, hit the line, moved right, went up, hit the line, moved right. What do we maybe do now? What if we start at the right side? And now we can go up and hit the line, and then what? Now we can go left by 1. Is that making sense? Okay. Uh-oh, did I mess this up? No, I didn't. Okay, there we go. Okay, so, well, let's go ahead and estimate the area of all these rectangles. So let's see. So we're going right by 1, and how far up for this one? 1. For this one, we're going right by how much? And up by how much? 2 squared is 4. So what's the area of this rectangle? 1 times 4, which is 4. Then this one, how far up are we going? It's going up 3 squared, which is 9. So it's 1 times 9. And for this last one, how far up are we going? It's going right 4 up 16. So that's 1 times 16. Okay. So let's find the area of all these guys. What's the area of the first one?
4, 9,
Okay. 1 plus 4 is? Plus 9 is? What is it? 14 plus 16 is 30. So this is an underestimate. What's this one going to be? An overestimate. Okay. Oh, oops. So this one is an underestimate. And this one is an overestimate.
I think I'm fine understanding what's going on in this class.
That's good.
2 minutes later.
What?
Okay. So this method that we just used, using rectangles to find the area of a shape.
Now, do we find the average of those 2 numbers?
Hold up, we're getting a little too far ahead.
No. I know now.
But that's a very good thing. That was one of the things I was going to ask next. This is called the rectangular approximation method. Now this method here on the left, which gave us an underestimate, this is the left-handed RAM. So it's rectangular approximation method, or RAM. So this one is left-handed RAM. And this one is right-handed ran. Okay, so why do you think this one's called left-handed?
Start from the left.
Because we started from the left, then hit the line and moved right. This one is the right-handed method because of rectangular approximation method. This is the right-handed one because we started where? On the right, moved up until we hit the line. Okay, make sense? Now this is actually when the computers are used to find areas of shapes. This is the way that they do it. They break it up into little chunks and find the areas of all these little chunks. Okay, so can anyone, but this gave us an underestimate, this gave us an overestimate. Can anyone think of something we can do to maybe get a better number? Do just a regular triangle? Break it up into triangles, but then we'd have like a triangle here, triangle there, triangle there. Doesn't seem like it's going to work very well for an estimation.
Find the mean average of the two numbers.
We can average them.
Yeah,
I think it was you, Jonah, a minute ago who said that? Add them up,
no,
divide by
it's
2.
me.
Yeah, you said average, and then he said add them up, divide by 2. So you both got the same thing. Sorry, that was talking really fast there. Okay, so you both contributed. Okay, can I erase this stuff now? Okay. Okay, so let's average those values. So how are we going to average them? How do we find an average? Mean average? I know you guys know it because you heard it a few minutes ago. I said it a minute ago.
RIM?
How can we find the average?
Add them up and divide by 2.
We can add them up and divide by 2. So what was our underestimate? 14. What's our overestimate? Then we divide by,
40.
then we divide by what? 2? Okay, what's 14 plus 30?
44.
44? Then we can divide by what? 2 to get 22. Okay. So that, what would that look like? If we were to do this geometrically, what would it look like to average these two values? Well, let's see. We're adding these up. So we're adding up each of these rectangles and then dividing it
That's the
by
answer,
2.
22. We solved it.
You think that's the exact answer?
Yeah.
I don't think it is. And I'll show you why. Okay, so the average is basically a slope, right?
Yeah.
Oh. Well, it's going to be adding them up, dividing that by 2. What we're actually doing when we take the average is we are instead of finding the area of rectangles, we're actually finding the area of trapezoids.
Close enough.
It's pretty darn close, isn't it? So what we're doing is we're taking the average of the two results. So here's our overestimate. I'll draw the underestimate in red. So you see how it's the underestimate with a little triangle perched on top of it to kind of fit itself in. So we're getting pretty darn close. We're getting pretty darn close, but is it perfect? let's see. Yeah, there's still, so when we draw the line here, there's still this, it's still this little bit here that's in between our estimation and where the line actually is. So is this an overestimate or an underestimate?
Over.
This is ever so slightly over our line, isn't it? So this method here, when we average the values, this is called a trapezoidal approximation. Can everyone say trapezoidal for me?
Trapezoidal.
I honestly just had you say that because it's really fun to say. Trapezoidal approximation.
Trapezoidal.
Okay. So we have a left-handed approximation, a right-handed approximation, and a trapezoidal approximation. Now this trapezoidal approximation is getting us pretty darn close in it, but it's not perfect. So I still have these areas missing, or these areas that are being either overlapping or underlapping, depending on the shape of my graph. What can we do to make those areas shrink? How can I make our errors go away? Uh-oh. Is that still recording? Oh, it is. It's going to be recording for another 3 minutes. We'll go ahead and do this for another 3 minutes, then I'll have to restart the recording again. So, what can we do to make these errors disappear?
Derivative magic.
Derivative magic, not yet. That's not until probably tomorrow. Okay, well it's kind of hard to see in the trapezoidal method because the error is actually really small there. Let's try looking at it with rectangles. So, let's say I have a curve like this. Let's find its area. Do you want me to use a left-handed or right-handed approximation? Just choose for me, left-handed or right-handed. Let's say right-handed. So we'll start on the right, go up to the line. Looks like I just hit the line. Let's say call this 4 right here. We hit the line and we go left. There. Go left by 1. Now I have to go up until I hit the line. Go left. Go down. Then I have to go right, or go up until I hit the line, go left, go down, go up until I hit the line, go left, go down. Okay? So we can see here that there are these big chunks out here that it's overestimating.
If you want to restart the recording.
We've still got 50 seconds, it's fine. So, and we also have these big chunks in here that it's missing. What can I do to make these chunks smaller? What can I do to make our approximation more accurate?
Can do it with left-handed approximation.
So if we do both, that's basically doing the trapezoidal. That would be us going up to the middle, to there, to there, to there. But we'd still have these chunks missing. Without changing our method, what can we do to to shrink those gaps?
I think your 50 seconds is up.
Okay. Wait. 5, 4, I'll stop right there. Okay.